See, I'm more stricken, but y'all niggas ain't stricken. Hold up. Hey, yeah, something wrong with it. If the money gone, we can be the fuck on with. I let my tape rock to my tape pop. I let my tape rock to my tape pop. It was all a dream. I used to read Word Up magazine. Salt and pepper and heavy D up in the limousine. Hanging pictures on my wall. Every Saturday, rap attack, Mr. Magic Molly Mall. I let my tape rock to my tape pop. Smoking weed and bamboo, sipping on private stock. Way back when I had the red and black lumberjack with the hat to match. Remember rapping Duke? The hard, you never thought that hip-hop would take it this far. Now in the limelight, cause I run tight. Time to get paid, blow up like the world trade. Born sinner, the opposite of a winner. When I used to eat sardines for dinner. Least the broad G, Brucey B, kick the break. Fuck flat, the flex, love, first start ski. I let my tape rock to my tape pop. I let my tape rock. Morning. To my tape pop. To my tape pop. Yeah.
Morning, everyone.
Beach with some ghetto ass gang in the club where she work and she poppin' that thing. Say the bread you can get it and they hit the ball. She can have a breathe on a nigga, you can make a ball. Come on, let her hope let it get but the ball. If they can't take off, they draw. I ain't standing down, nigga, no. I know the way she paying, she look like she fucking herself. So they do a number just touch herself. Freaky ways, she can shake ass for days. Kick it in 69 different ways. The whole thing, she get paid to go long. They got enough money, she taking the gold off. I know I put it. I be like, that's top of the line. You face little waist for the big behind. You die. That's top of the line. You face little waist for the big behind. You die. That's top of the line. You face little waist for the big behind. You die. That's top of the line. You face little waist for the big behind. I stay strapped like car seats, been banging since my little nigga Rob got killed for his ball. That's 10 years I told you in 95, I killed you if you try me for my Air Max 95. vibes. So base when I met him, I'm around. If I gotta die, rather homicide. I ain't actually saying my grandmama died. Then I'm going back to Cali with my Jacob boy. See how time was. And I'm gon' shine on me until my heart stop with that MVP. I'm black 70 feet, and I ain't going nowhere. So if you know it, nigga, the underdogs on top. And I'm gon' shine on me until my heart stop with that MVP. I'm black 70 feet, and I ain't going nowhere. So you get to know it. Get to know it. Get to know it. Get to know it. Get to know it.
Morning, everyone.
Have it like that. You gotta 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 have it like that.
All right, good morning, everyone. This goes on for another half hour or so. Got to stop somewhere. Good call on the girl talk there. Very nice. For those of you interested, as stated, this is girl talk. DJ, mashup artist. Wonderful stuff. Yeah, I was actually going to play Grand Van on Monday, and then I felt like something else. Maybe on Friday. Maybe on Friday. For those of you unfamiliar with Grand Van, James DeSalvio. Is music royalty in Montreal. EXP is the exponential, exactly. EXP of X is e to the X. There was question about the midterm material. Midterm material goes up to and including the chain room. I'm going to post the actual sections. I forgot to do that on Monday. I'll do it after class. Somebody remind me, somebody send me an email in case I forget. I left you with the following question last time. Why radian measure? It's a valid question. You know, I mean, you learn it in high school and they don't really tell you why. So now let's see why. Right? I mean, we saw that if theta is measured in radians, the derivative of sine of theta is cosine of theta. I don't know how many questions, I haven't written it yet. Probably around 10 or so. I forget what we started with, but I mean limits, really, limits moving forward. right? So if theta is measured in radians, we suggested that the derivative of sine is cos. If x is measured in degrees, the question is, what is the derivative of sine x with respect to x? Well, let's switch to radians. Let's switch to radians. There will not be any specific pre-calculus questions on the midterm. But you understand that if you don't know pre-calculus, it's going to be difficult to work with these functions. So while there will be no specific pre-calculus questions on the exams, you still need to be very comfortable with that material. So, as Eddie suggests, while I won't write that down immediately, if theta is measured in radians and x is measured in degrees, we're looking for the derivative of sine x and convert to radians. And now chain rule tells you that this is the derivative with respect to theta of sine theta times the derivative of the inside with respect to x. This is the chain rule. And as Eddie has suggested, theta is really degrees to radians. Oh, I was offline for a second and now I'm back. Is everybody still here? Let me give you a moment. Yep, thank you. Thank you. Very good. So there you have it. The derivative of sine theta with respect to theta is cos theta. And this d theta dx is pi over 180. So in other words, pi over 180 cosine x. And that's why you want radian measure. That's why radian measure is desirable. Because in degrees, the derivative of sine x is pi over 180 cosine x. You've got this extra business happening. There it is. How are we doing? So that's why you want radian measure. That's why radian measure is desirable, because everything is nice and clean. Of course, we just did it for sine, but you can do it. It's still the same section. Still the same section, page 206. Now, let me give you why is the derivative of sine x not cosine x? Because x is measured in degrees. I mean, the proof is right here. If x is measured in degrees, the derivative of sine x is not cosine x. In radians, the derivative of sine is cos, but not in any other coordinate system. Well, that's why we always work in radians. To have this
cleanliness. Well, all I'm saying is switch to radians, right? Theta is measured in radians, so for every value of x, you have a corresponding value of theta. And I mean, it can be found this way. Is there a reason for that, for this? I mean, I think we convinced ourselves by looking, right? I mean, how are radians defined? Radians are defined where if you have a radian h here, this arc length will be h as well. And that's how radians are defined, and they're defined for exactly this reason. So that this height and that behave in the same way as h goes to 0. Right? Can you imagine carrying around this pi over 180 and all the work that you do? That's why radians were sought out. Elliot, Elliot, I'm not sure I understand what's happening, what you're asking here, but all I'm saying is it's an application of the chain rule. And, well, all I'm saying is theta is the equivalent. This is how you transform theta versus x. It's just switching to radian measure. How we arrived here? Well, all I'm saying is if think of your calculator. You've got a degrees versus radian button. If you plug in 45 degrees and you calculate cosine of 45 degrees, you're going to get an answer. And if you calculate cosine of pi over 4 in radian measure, you get the same answer. That's all I'm saying. d theta by dx, treat this as pi over 180 times x. No need for quotient rule. You can do the quotient rule if you want, but it's just a constant times x, whose derivative is just that constant. Remember a question like this, where you had to find values of a and b for which the function was differentiable at 0. Not yet, but after this example, right? And what a lot of people want to do is they want to take the derivative of this, take the derivative of that, and then take the limit as x goes to 0. And I suggested that does not work. I mean, it might work in this example, but it doesn't always work. So if it doesn't always work, you shouldn't do it. And we're now ready to see an example where it does not work. Consider the function x squared sine 1 over x. consider this function. Let's talk about this function. Well, I mean, here's the question. Where is this function differentiable? Oh, is that right? Oh, that's a good question then. Maybe I won't do it. Well, I mean, let's talk about it. It's a good place to talk about it, and plus it's a challenge question, so yeah. I think it's an important question, so let's discuss it. Where is this function differentiable? Well, as critique suggests, without doing any work, x squared is differentiable, sine is differentiable, 1 over x is differentiable, everywhere except at 0, right? You know the derivative everywhere except at 0, because you get a minus 1 over x squared. Exactly, as Connor suggests, right? If we're not told if x is degrees or radians, it defaults to radians. Everybody uses radians. Nobody uses degrees unless it specifically tells you it's degrees. So the default is radian. So here we're in radian measure, of course. And yeah. So without doing any work, f is differentiable everywhere except perhaps x equal to 0. And why don't we talk about the derivative for values not equal to 0? What is the derivative for values different from 0? Well, I mean, for values different from 0, this is your function. So let's differentiate this. And how do we differentiate? You see that it's a product, so product rule applies. 2x sine 1 over x plus, leave the first one fixed, differentiate the second one, derivative of sine is cos, times the derivative of the inside, chain rule, right? Which is 2x sine 1 over x minus cosine of 1 over x. Thank you. There it is. So, you see, if we make a parallel with the first example, where people want to take a limit as x goes to 0, what is the limit as x goes to 0 of this business? Well, let's look at the first part. Let's look at this business. Sine of 1 over x is always between -1 and 1. Adele, where did I lose you? Theta is pi over 180 times x. So d theta dx. This is just a constant. We'll leave it out. And when we differentiate the x, whose derivative is 1. If x is, well, so, right, I mean, we know this, we've used this many times, and so you're going to multiply the whole thing by 2x, and now the result of the product is questionable. It's either going to be minus 2x, less than that, less than 2x. This is true if x is bigger than 0. Or, if x is less than 0, the inequality switches. But in any case, why are we using the limit here? Because that's what a lot of students want to do. They want to take the derivative and then take the limit as x goes to 0 to get the derivative at 0. And this is the simplest example, if you will, where it does not work. As x goes to 0, what's happening? This goes to 0. This goes to 0. So the stuff in the middle goes to 0. And similarly on the other side. This goes to 0. This goes to 0. So the stuff in the middle goes to 0. So by the squeeze theorem, this part goes to 0. But what about this? As x goes to 0, well, let's say 0 from the right, 1 over x is going to go to infinity. And what's happening to cosine as you approach infinity? This does not exist, exactly. So this part does not exist. So we saw a nice result that if the limit of one part exists and the other one does not exist, then their sum does not exist. So the whole thing does not exist. Now, somebody pointed out, I think it might have been Eddie, or maybe somebody else, who knows. That result that I gave, that we proved in class, was only valid for finite limits. Right, so be careful. Only true for finite limits, but that's what we have here. Here we have a finite limit, and here we have a limit that does not exist, so the whole thing does not exist. And some people, I think I'm confusing a lot of people here. Consider this example. Consider this example, and my question to you is, what is f prime of 0? What is f prime of 0? And what a lot of people want to do is say, well, the derivative is 2x for x not equal to 0. And then it's 3x squared for x bigger than 0. And at 0, they're both 0. So the derivative is 0. right? Take the limit of this as x goes to 0, take the limit of that as x goes to 0, and there's your answer. I'm saying that does not work. And our example is this one. This is the example that contradicts this. Right? Here we took the derivative, and we see that the limit does not exist. So what should we do instead? Pratik is asking a good question. You have to always go with the definition of the derivative. And, you know, as Andy points out, that's what a lot of people want to conclude. A lot of people want to conclude that the derivative does not exist at 0. But it does exist. And let's calculate it, right? So here, this limit does not exist, but the derivative at 0 still exists. You have to resort to the definition. F of h, when h is not 0, is this. H squared sine 1 over h. F of 0 is 0 over h. And this is just h sine 1 over h, which goes to 0 by this similar, by the squeeze theorem. So in fact, this function is differentiable everywhere. So what is this an example of? This is an example of a function whose derivative is not continuous. Exactly. Sine of 1 over h does not exist, but the h makes it go to 0 by the squeeze theorem. No. That's not how the derivative works. If you know the function at one point, you cannot conclude anything about the derivative. You don't plug in the point first and then take the derivative, but rather the other way around. Look, I mean, we calculated the limit essentially right here with x instead of h. Right? It's the same thing without the 2's. Get rid of the 2's. It's a squeeze theorem. So this means the function is differentiable at 0, but not continuous at 0. Exactly that. So it is, wait, Ava. The function is continuous everywhere. The function is differentiable everywhere, but its derivative is not continuous at 0. All right, very nice. Moving on. How can it be differentiable at 0 if the derivative is not continuous at 0? Well, we don't have a theorem that guarantees the derivative is continuous. And in fact, this function is an example of a function whose derivative is uncontinuous. What are we concluding based on this idea? We're concluding that you cannot take the limit of the derivatives and conclude that the derivative at 0 is whatever is based on the limits. If it is differentiable at 0, does that mean that f prime is continuous at 0? No. This is the counterexample. The derivative of this function is not continuous at 0, even though the derivative exists at 0. All right, let's move on. I mean, Zuhair is asking why, but we just spent 15 minutes showing why. This is still chain rule, right? When you differentiate this, you apply the chain rule. But I mean, it takes everything into account, right? Chain rule, limits, limit definition, squeeze theorem. It's a beautiful question. Can we illustrate the graph of the function? I don't know that it's going to help. No. I can't. Not really. No. Well, I mean, all I could say, what could I say? You know the graph of x squared, you know the graph of negative x squared, and since you're multiplying by this, which alternates between -1 and 1, as you go towards 0, it's going to be somewhere in here. And it's 0 at 0. Gabrielle, I'll have you look. I claim the limit from the left and the limit from the right do not exist. That's why it's not. That's why the derivative is not continuous. All right, let's move on because we have to get to implicit differentiation. Here's what we've been doing so far, right? I've given you a function and we've differentiated it. Nice and easy. What if, instead of giving you a function explicitly, right, y equals some function of x, what if I gave you an equation involving x's and y's, where theoretically you could solve for y as a function of x, but might not be able to do so in practice? Can we still ask for the derivative of y with respect to x? The answer is yes. And this is the idea of implicit differentiation. Where function where y is not given explicitly as a function of x, but rather implicitly, where you have an equation involving x's and y's. Let's illustrate with an example. Consider this. Implicit differentiation will not be on the midterm, but everything we've done before is material that you're responsible for. Right? We have this equation involving x's and y's. We have not solved for y as a function of x. Perhaps we can, perhaps not. I was not planning on having a midterm review. Let me suggest this. The day before the exam, come armed with questions. If you have questions, we can answer them in class. If you don't have any questions, we'll do new material. So, right, I mean, you don't have y as a function of x. You can try to solve for y here. Sure. You can try to solve for y, but let's not do that. And instead, let's assume that it can be done. Assume that you could solve for y as a function of x. Assume y can be solved for as a function of x, and then we ask the question, what is dy dx? What is the derivative? What we're going to do is differentiate the whole equation with respect to x. Differentiate the whole equation with respect to x under the assumption that y actually is a function of x. Eddie is suggesting some good stuff there. You might be able to solve for y as a function of x by doing some tricks. Let's put that aside for a moment and just differentiate the whole equation implicitly. So this is what implicit differentiation refers to. It's when you assume y is a function of x without explicitly solving for it. So if we differentiate the whole equation with respect to x, derivative of 2x squared, you know what that is. That is 4x. Derivative of xy, well, now you've got a product, right? Because you have assumed y is some function of x. So you have x times a function of x. So the derivative requires the product rule, differentiate the first one, leaving the second one fixed, plus leave the first one fixed, differentiate the second one. What is the derivative of y? Well, the derivative of y is exactly dy dx. We don't know what y is. Y is some function of x. We don't know what it is. There it is. Derivative of y squared? Well, that's something squared. So differentiate the square and then differentiate the inside. Inside is y, whose derivative is, once again, dy dx. Chain rule, very nice. Derivative of 2 is 0. Leave all the dy dx's on one side, bring everything else to the other. Factor out, you can write y prime instead of dy dx. You know it's an equivalent reformulation. Factor out of y prime. And so you see that dy dx is minus 4x minus y over x minus 2y. So you have the derivative, you have dy dx, even though you did not solve explicitly for y as a function of x. This comes at a cost, as you can see, right? The derivative will have both x's and y's. Instead of just the usual x's that you would have if you were able to solve. It's not really a big deal. Where did the x dy dx come from? This is the product rule, right? It comes from the derivative of this. Differentiate the first one, leaving the second one fixed. Plus, leave the first one fixed, differentiate the second one. Derivative of y is dy dx. Can we assume y equals a function of x, or does it have to be given? You can assume. You can assume. And the question comes up naturally, when is this true? And the answer comes to us via the implicit function theorem. You can solve for y as a function of x if this denominator is not 0. So the implicit function theorem tells us that you can always solve, at least in theory, for y as a function of x, as long as this denominator is not 0. Y, what about the 2y dy dx? Well, what do we have here? So this comes to us from the derivative of this, and what is this? This is something squared. So we differentiate the square first, we get a 2y, and then you differentiate the inside, the chain rule. Derivative of y is dy dx. And Ashir is suggesting that you could actually solve for y here. And that's a beautiful observation, right? Let's rewrite that right here. A beautiful observation if you, Ashir had suggested to complete the square. Instead, I'm going to suggest that we bring everything to one side, and we get y squared minus xy minus 2x squared plus 2. And completing the square certainly works fine. But if you take a step back, you recognize that you have a quadratic in y. Very nice, Eddie. A quadratic in y, so you can use a quadratic formula because you're looking for zeros. You're looking for roots of this quadratic. So using the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a, or if you prefer, this is 8, so 9x squared minus 8 over 2. And here's the beautiful thing. So Eddie got the same answer by completing the square. Very nice. And here's the nice thing. If you choose one of these, either the plus or the minus, whatever you want to do, take one, differentiate, right? So why don't we do that? If you take one, let's take the plus, and you differentiate. First, let me take the 1/2 outside. The derivative of x is 1. The derivative of square root, 1 over 2 square root, times the derivative of the inside, which is 18x. So that is 1 plus 9x over square root of 9x squared minus 8. So that's the dy dx, but we had already worked it out here. Except that our answer had x's and y's. If you plug in the y into this, Rachel, quadratic in y, right? Y is the variable we want to solve for. So a y squared plus by plus c, right? ay squared plus by plus c is equal to 0. That's what we have here. So y is negative b plus or minus square root of b squared minus 4ac all over 2a. We're just using the quadratic formula, noticing what you have here is a quadratic in y. If you plug that value of y into there, what do we get? Y is x plus the square root. These twos cancel, then the x will cancel, leaving you with what? Put everything over common denominator, 8x minus x minus the square root. The whole thing over 2. And in the denominator, you just get a negative square root. So let me get rid of all the negatives and bring the 2 down. And we get a plus square root of 9x squared plus minus 8 over 2 square root 9x squared minus 8, which hopefully is the same answer. Eight plus 1 is 9. And it's 9x, geez, what's going on? 8x plus 1x is 9x, and now that's exactly the same answer as we had. 9x, thank you, Eddie. So if you use implicit differentiation on the final, you can leave everything in terms of y, that's fine, no problem. And in most cases, dealing with implicit differentiation, you're actually not able to solve in practice. But if you are, then the answers will agree. How are we doing? Let's take another example. So this, yeah, same page, 214. Right, so here's the question. Find dy dx given this equation. What are we going to do? We're going to differentiate the whole equation with respect to x, assuming y is a function of x. Right? Notice here that while in the previous question we had a quadratic in y, so we could actually solve for y. Here you've got a cubic. You'll be interested to know that there is a cubic equation, very similar to the quadratic equation, which takes up the whole line of a board. It's very long, not as compact as the quadratic equation, but I mean there is one out there. So you could actually solve for y as a function of x. Let's just assume, though, that it could be done and differentiate the whole equation with respect to x. Derivative of x cubed, 3x squared. Derivative of xy squared, it's a product. So product rule applies. Differentiate the first one, leaving the second one fixed. Plus, leave the first one fixed, differentiate the second one. Second one is something squared. The derivative is 2 times that something times the derivative of the inside. Chain rule. Derivative of y cubed, 3y squared times the derivative of the inside. Derivative of 1 is 0. Expand, leave all the dy dx's on one side, bring everything else to the other. So bring this to the other side. Factor out a dy dx from the remaining stuff. And you see that dy dx is this. Exactly that, as the review suggests, because we consider y as a function of x, the chain rule applies. Pratik, I think our answers differ. I had an X there. Do we have to restrict the denominator to be non-zero? Actually, again, right, the implicit function theorem tells us that you can write y as a function of x as long as the denominator is non-zero. So, yeah, I mean, you could say an extra step, assuming that denominator is not zero. I mean, I'm not going to necessarily be looking for that. I'm not going to deduct marks unless I specifically ask. So you can just assume it, yeah. Shall we do one more? One last one? We are already a bit over time. A quick one. Same question. Now there's no hope of explicitly solving for y as a function of x, right? There's no way you're going to isolate y on one side and just have x's on the other. You can try. Convince yourselves. Right? This is x e to the y is equal to x minus y. But let's assume that it can be done in theory. So we assume y is a function of x, and we differentiate the whole equation with respect to x. So here you have a product. Product rule applies. Differentiate the first one, leaving the second one fixed. Plus leave the first one fixed, differentiate the second one. Second one's an exponential. Derivative of e to the something is e to the something times the derivative of the inside. Differentiate the right-hand side. Derivative of x is 1. Derivative of y is the derivative of y. Bring the dy dx's to one side, everything else to the other. Factor out the dy dx and divide. There you go. Sophia's asking what's the derivative of e to the y? Well, the derivative of e to the something is e to the something, and then you differentiate the inside. Derivative of y is the derivative of y, dy dx. Elliot's asking an excellent question. What if we decided to set x as a function of y? Then you could ask the question, what is dx dy? Very nice question. Then, is there a relationship between dx dy and dy dx? Another great question. It seems that they should just be reciprocals of each other if the notation makes sense, right? Because this is just notation. I mean, it's not an actual fraction. But it does turn out to be that way. Very nice. In some situations. And yes, so in some situations, dx dy is 1 over dy dx. Maya is asking, the question was the difference between d by dx and dy dx. And I mean, it's a question that a lot of students had. I think we answered it a while back, but let's discuss it again. D by dx is the action of differentiating. This is the verb, right? I'm going to differentiate this equation. Dy dx is what you get once you've differentiated. It's the derivative. What I mean by 1 over is that it might not be exactly what you would expect. I mean, who was it? Elliot? Elliot suggested. So take this example. Take this example and differentiate with respect to y instead. See what you get. In terms of x and y, and see if it's exactly what you were expecting. All right, but that's enough. We've overextended our welcome here. Thank you all for coming, folks. Practice this implicit differentiation. We'll do a bit more on Friday and move on from there. Thank you all for coming. I will see you on Friday.